NTT Corporation, Japan. I'm very happy to be here, and I'd like to thank organizers for such an interesting workshop. And this work is done with the collaboration with Hiroyasu Tajima with equal contributions. And after we submit this talk, we realized that today I would like to talk about resource theory of asymmetry for finite commutative groups, especially about the IID conversion rate. But after we submit, we realize that we can generalize our results to the general finite groups, which is generally non-commutative. So I will also present the results for finite groups. So this is the outline, and so I will first talk about the review of resource theory of asymmetry. So the study of resource theory of asymmetry presents from the theory of reference frame. Suppose that two parties don't share the reference frame. For example, Alice and Bob do not have a shared phase reference described by U1 symmetry. And when Alice sends the quantum state to Bob, which is asymmetric, then Bob obtain partial information on phase reference of Alice, depending on the degree of asymmetry. So this is the left figure is the vacuum state, a Wigner function of vacuum state, and this is totally symmetric under rotation, so it does not contain any information on the phase reference. But if Alice sends coherent state, then Bob can obtain some information on phase reference. So the natural question is how much information on the reference frame can be shared by sending a quantum state. And more generally, we can ask what task we can do under symmetry constraints. And the resource theory of asymmetry is a good framework for studying this problem. So we suppose that the system has a symmetry described by group G. And the action of the symmetry transformation on the system is described by the projective unitary representation of G. So the psi becomes UG times psi. And yes, and G, and this is a representation. So the successive application of these operation, unitary operators is consistent with the group operation. In this setting, we define the symmetry of a given state, which is the set of elements that does not change the state rho. And using this symmetry, we can define the free state, where this symmetry of the state is the whole G. This means that the state does not change under the symmetry operation. So in this sense, this is totally symmetric state. And free operation is defined as the G covariant operation. This means that this operation is commutative to any symmetry operations. And yeah, this is something about mathematics. Any unitary representation can be decomposed into direct sum of irreducible representations labeled by mu. That's this. This means that UG can be block diagonalized for all G in group. And here we consider commutative, let's consider a commutative group G. Then all irreducible representations are one-dimensional. Then pure state is characterized by the probability distribution on mu, defined by this. And so this is the weight on the subspace of mu. For example, when the system has the parity symmetry described by Z2, then irreducible representations are odd and even under the parity transformation. And also, when G is U1, then the representation corresponds to the, has the value of integers, and it corresponds to the Fock level in harmonic oscillator or angular momentum. And the single copy transformation between pure states. So pure states psi is completely characterized by some probability p, and phi is described by q. Then it is known that transformation from psi to phi by G covariant operation is possible if and only if for G equals Z2, this asymmetry measure is non-increasing. And also for U1 case, sufficient necessary condition is known that there is a probability distribution W such that P is the convolution of W and Q. And but for general group G, representations are irreducible representations are not necessarily one-dimensional. So the state cannot be characterized by a probability distribution in general. However, there is a very useful quantity that is characteristic function, which is defined by this. Then Marvian and Stekens show that the transformation from psi to phi by G covariant operation is possible if and only if there is a state rho such that the characteristic function of psi can be decomposed to that of rho and phi. Actually, this paper is very nice, and we use these results from this paper many times. And also there is some result on IID conversion rate. And we consider two types of conversion rate. One is exact one, and another is the other is approximate one. So in approximate one, we consider the vanishing, the conversion under G covariant operation with vanishingly small error. And when symmetry is Z2, the exact rate is known to be the ratio of this quantity. And also for U1 case, it is known that the approximate rate is given by the ratio of variance or quantum Fisher information. So far, IID conversion rate are known only for Z2 and U1. So they are the simplest group, discrete group, and simplest continuous group. And there are natural questions such like why do we consider exact transformations for Z2 while approximate ones for U1? And also another question is that for general G, we do not know RTA counterpart of entropy in N-3, which determines the conversion rate between IID and pure states. And we try to answer these questions. And for first questions, we show that when G is finite, the approximate IID transformation becomes trivial. In the sense that the conversion rate becomes either infinite or zero. And for about the second question, we show that a set of asymmetry measures determines the exact conversion rate for finite group G. So let's consider the finite commutative group case. You may think that the finite commutative group is too simple, but it actually contains very important example, such as stabilizer groups, which is the n-fold product of Z2, and also recently rotationally symmetric bosonic poles are well studied. Here, the stabilizers are the isomorphic to ZA. So this means that we consider the state with A-fold rotational symmetry. These fixtures are correspond to the four-fold rotational symmetry. And in general, any finite commutative group has a canonical form like this. This is known as the fundamental theorem of finite commutative groups. And here, G is isomorphic to cyclic groups. And here, Qi divides Qi plus 1. This constitute, intuitively, this is a finite lattice with periodic boundary condition. Here we consider this form of symmetry without this condition. And for such a group, irreducible representation is added by a point of the reciprocal lattice G hat, but this is isomorphic to G, like this. And so this means that the space of conserved quantity is finite and periodic. But this is very different from the U1 case. In U1 case, the quantity space of conserved quantity is integers, space of integers, so infinite. But for finite commutative groups, it is finite. And since this is representations are one-dimensional, pure state is also characterized by a probability distribution P on lambda. And we can show that a similar statement to U1, like a pure state can be transformed to psi can be transformed to phi by G covariant operation if and only if there is probability distribution such that P is a convolution of W and Q. And yeah, so let's consider the IIDs. So let's consider IID state. So for psi, the probability distribution for the n copies of psi is given by the n-fold convolution. In terms of the characteristic function, we can check that this characteristic function is a Fourier transform of the probability distribution. So in this Fourier space, the convolution is replaced by just a product. So the characteristic function of IID state is just a nth power of single state. And we go back to the probability distribution, then it can be represented like this. And the first term is a convolution from the A equals 0. And when this characteristic function is smaller than 1, then only this 1 over G terms survive. So it converges to uniform state. To state this phenomenon more precisely, we consider so uniform state with symmetry H. Here H is a subgroup. Then this state is defined as a state with the characteristic function defined like this. And under this definition, we can show that the IID state of psi can be approximately transformed to the uniform state with the same symmetry as psi, with an exponentially small error. We get the proof, but yeah. And second, we can prove another theorem that states from the uniform state with symmetry H, an arbitrary number of arbitrary states can be exactly obtained by G covariant operation if H is included in the symmetry of phi. We also skip the proof. And combining this theorem, we can show that psi can be approximately transformed to uniform state, and the uniform state can be exactly transformed to any arbitrary number of arbitrary copy of state. And this M is arbitrary, so the rate, approximate rate, is either infinite or zero. This is why we need to consider exact conversion in the case of finite symmetry. And we compared the case of Yuan. Mathematically, it is known that when G is commutative and locally compact, the relation between symmetry G and the space of conserved quantity G hat is not described by the so-called Pontryagin duality. And it is known that G hat is compact if and only if G is discrete. This means that when G is discrete, G hat is compact. This means that there is a finite Hall measure on G hat. This means that IID state converges to the uniform state. And this uniform state has infinite resources. On the other hand, for U1 case, G is continuous. So G hat is non-compact and there is no uniform state. This is why approximate conversion is non-trivial in U1 case. So we consider the exact IID transformation. And first we show that we introduce asymmetry monotone, L. This is minus log of absolute value of characteristic function. And actually, this is asymmetry monotone. And since this characteristic function takes a value between 0 and 1, L takes a value between 0 and infinity. And we define this subset of G, where the symmetry with 0 resources or symmetry with infinite resource. Then we can show that exact conversion rate between two IID pure state is given by this. So again, we have a ratio between two measures, but we need to take the minimum over elements of G. This is in contrast to entanglement theory, where the rate is determined by a single quantity, entanglement entropy. In this case, the conversion rate is not determined by a single quantity, but by multiple quantities, like this. And in general, since there is a minimization, in general, the exact IID conversion is irreversible. And we need to carefully treat the case of L takes a value of 0 and infinity. This is why we need some conditions on this and some exclusion in this in minimization. And this is a sketch of proof for direct part. So we show that when R is smaller than this minimized value, this rate R is achievable. And you use the fact that, again, you use the fact that pure state can be transformed to another phi by G covariant operation if and only there exists the probability distribution satisfying this. This condition can be explicitly rewritten by carrying WK like this. And here we have a positive part and some another part. And since this ratio becomes exponentially small if R is smaller than this value, this quantity vanishes and WK becomes positive. So W becomes probability distribution positive, and this R is achievable. So rate is equal or greater than this quantity. For converse part, when rate R is achievable, using the monotonicity and additivity of L, we can drive this inequality. So this is monotonicity and these equalities are additivity. And from this, we can show that achievable rate is always equal or smaller than this quantity. Combining direct and converse part, we can show that the exact conversion rate is equal to this quantity. Finally, we briefly show the result for general finite group, which is non-commutative. Actually, for approximate conversion rate, we can show this. We have the same result as the commutative case, like this. And also, we could show that when the symmetry of psi is contains only identity, then the same expression as the commutative case holds. This condition means that psi has a non-zero asymmetry for any G, except for identity. Sorry, we skipped that proof of this, but yeah, we can generalize the result to the non-commutative case. This is conclusion. And okay, thank you for listening.
Thank you for this very nice talk. Other questions in the audience? Yeah.
Thanks. So you mentioned that that there is a connection with stabilizing groups, for example, that they are always commutative and so on. So are states with asymmetry somehow useful in error correction folds or something like
that? Actually, I try to consider the application to error correction fold or some resource theory margin for something. But yeah, it seems that this formulation is not suitable for explaining error correction folds as long as I consider it.
Any more questions? No, I don't have one. So if you have a finite group, then there's a sort of universal resource in this resource theory by extension. Namely, you take the left regular representation and just take one of the basis states, right? If you take it as a resource in this resource theory of finite groups, the system with the left regular representation of your group, and you take, say, the state associated with the identity element, then this is like a perfect resource. Can you comment on whether I can think of this asymptotic limit as something converging to the left regular representation in some? So it seems that the state that you get out is basically that. But maybe I'm misunderstood something.
So I'm sure what left.
Or you take the Hilbert space, which is spanned by the elements of the group, as an orthonormal basis, and then the group just acts by multiplication.
I see. But we, as,
It seems to me that this infinite tensor product is in some way contains this asymptotically, but maybe we can discuss this offline.
so
Other questions? If that is not the case, then everybody's hungry and wants to go to lunch. So let's thank the speaker again and we can go.